Welcome everyone to today's colloquium. And today we're very happy to have Chia-Yu as our corporate speaker. So Chia-Yu got his bachelor degree from NTU Material Science, and then he did the astronomy master study at NTU, and then he moved to MPE for his PhD study. After that, he had a few postdoc appointments. First one is at CCA, the Flatiron Institute in New York City, and then moved back to Germany at MPE as his second postdoc. And then about a year ago, he moved to the US again, to the University of Florida. And so today, Chia-Yu will tell us about hydrodynamical simulation, especially for comparing the resolved supernova feedbacks in different numerical codes. Let's welcome Chia-Yu.
Okay, thanks for coming. So today I'm going to tell you about the recent project we're doing on about the code comparison in resolved high-resolution simulations under the context of the SMAUG collaboration. The SMAUG collaboration is a multi-institute effort to try to integrate these small-scale simulations, put it into as a separate discussion for the next generation cosmological simulations. So this is part of that effort. So the current state-of-the-art simulations in galaxy formation is using cosmological simulations. That means starting from the initial conditions predicted by the CMB, and you're putting all the physics you know, and the gravity will collapse, the gas will collapse into halos, and the galaxy will form within those halos. And within those halos, you put in the ISM physics you know, and then you can grow galaxies self-consistently using these kind of simulations. And these simulations have been very successful in recent, the last decade or so. Nowadays, these large-scale simulations are capable of reproducing galaxy properties such as their sizes, their masses, and their luminosities. So it's really a remarkable success for these simulations. And this has been the industry standard to study galaxy formation theoretically. However, there are some limitations for the current cosmological simulations, which is the so-called subgrid model, that's the physics that you cannot resolve. Currently, the state-of-the-art simulations for uniform boxes, you can go to about 100 parsec or so. You can maybe go to an order of magnitude more, to around 10 parsec, if you do zoom in to individual galaxies. But the ISM physics happens at much smaller scales, around parsec or even sub-parsec scales. And because the small scale physics are not resolved, we have to put in some subgrid models to mimic the unresolved physics. And this is an example of the famous illustrious DNG. You can see galaxies of different types are reproduced reasonably well. The problem of using subgrid models is not because they are subgrid, but it's actually because the methodology. So the subgrid models, they are motivated by physics, but however, there are some free parameters that you can play with. And these free parameters, there are no physical, or there's no unique way to tune these parameters. So what happens is people usually tune the free parameters to reproduce certain observations. For example, the most commonly used one is the galaxy luminosity function. And you tune your parameters such that these key observations are reproduced. And then you look at other properties like mass and metallicities, etc. And those will be your predictions. But however, there's always a bit of ambiguity because of this methodology, that sometimes you don't know what is your input and what is the actual model prediction. So here is just an example of the free parameters in the supernova feedback in investors. you can see there's a number of free parameters that you can choose, and the values of these parameters and the functional forms are very ad hoc. So they are designed physically motivated, but to determine these values, you have to tune to observations. And so Illustrator is not the only way you can do cosmological simulations. There are a bunch of different groups that are working on cosmological simulations. For example, the fire simulations, Nihao, these two are zoom-in type of simulations. And the SIMBA, Horizon AGN, and Magneticons, these are more large-scale uniform boxes. They all doing subgrid models in slightly different ways. However, the problem arises when these models predict very different results, which they do. For example, this is one of the code comparison project in the Aquila cube simulation project. If you compare all these different types of these different cosmological simulations, you'll see vastly different results in this gas fraction as a function of luminosity. And more importantly, among these different models, a number of them are actually using the same code. They are all using Gadget. They're just different in their subgrid models. But the results are very different. So it's very hard to judge which one is the right one, which one is the correct one. So it has become a very philosophical or religious debate whether which models is most accurate. So the analogy I like to use is to ask which rice dumpling you prefer. So it depends very much where you're from and what you believe. One of the key subgrid physics that needs to be modeled is the sort of supernova feedback. Here's a recap of the evolution of the supernova rampant. So when a supernova is injected into the surrounding ISM, the first phase is the so-called blast wave, the so-called state of Taylor phase, where the thermal energy of this supernova is converted into kinetic energy due to this pressure force. And as it evolves, at some point, radiative cooling kicks in, so the energy is radiated away in a bubble. The energy in the shell is radiated away first, because that's the densest gas, where cooling is efficient. And then you form a shell with cooled gas, and this is where you start converting energy to momentum. So the momentum becomes conserved. You just keep sweeping up the mass. And if you want to resolve this supernova feedback, you need some resolution to resolve that. Here are three different resolutions. This is 10 to the minus 2 solar mass per particle. In the middle panel, you see 1 solar mass per particle. And the right panel is 100 solar masses per particle. And if I just inject this supernova energy in a uniform medium, try again. Well, you can see that these two resolutions, they are more or less similar. So you do resolve the supernova injection and the conversion of the momentum. But in the right panels, you see that the energy you injected is, first of all, is injected into a much larger area than it physically should. And that's why most of the energy is radiated away, because the energy inject will heat the gas to a temperature where cooling is most efficient. This is a so-called overcooling problem, and that happens when you don't have the resolution to resolve supernova feedback. So in order to resolve feedback, you really need to properly capture the state of Taylor phase where the momentum is being generated. So quantitatively, this means that the radius where cooling becomes efficient is a so-called cooling radius. And this radius has to be resolved. This gives a spatial scale that needs to be resolved. And you can notice that this depends on density here. And that's, so if your supernova explode in denser gas, the radiation cooling will happen faster. That means that it's more difficult to resolve supernova that happens in dense environments. And if you have a Lagrangian code, you have a mass resolution. You can convert this to a swept up mass where cooling happens. And this is roughly this scale. It also has a density dependence. And if you model this idealized setup in a systematically decreasing, downgraded resolution, you'll see that at around 100 solar masses or so, you stop resolving supernova feedback, and then as a result, you don't capture the kinetic energy or the momentum generated by the feedback. And these kind of idealized tests have shown that under typical ISM conditions, we need around 4 parsec resolution if you have an Eulerian code, or if you have a Lagrangian code, you need around 5 solar mass per particle.
So, Jack, I have a question about when you say the explosion, you dump the energy into the. Do you also add the mass of the star, supernova ejecta?
Yeah, the ejecta is also injected into the ISM, but that's a very small amount.
Yeah, but in that case, the resolution here you need is you need to resolve at least this small for the blast wave or for the region of the explosion. How do you say this?
So actually, the ejecta mass is not very important in this case, because all you need to have is to resolve the ambient ISM. So you can eject mass, or you can choose to not eject the mass to the ISM. You'll still get a similar result. So the key is to resolve the ISM, not the ejector.
Yeah, I see.
How about density? Density dependence.
Yeah.
You assume ambient density of 1.
That's right. That's right.
You don't have such an interstellar medium. It depends on whether your supernova was type 1A or core collapse. If
Sure,
the core
yeah.
collapse, the stellar wind has already evacuated all the gas around it. So it's a
Right.
cavity explosion. The density is not 1.
The
So-
density. So 1 is a representative density for that. It actually can, as I'll get to later, it actually have a range of density where supernova occurs. It goes from
Supernova are usually clustered because massive stars are born in clusters.
Exactly.
So one after another, first you form a superbubble, then the subsequent supernova explodes in cavity.
Yeah, yeah.
Low density medium with a
That's right,
point
that's right.
1 or something.
Yeah, so those supernovae will be actually easier to resolve because they explode in lower density gas.
So do you keep track of the history, interstellar medium?
We keep track of the ambient density where supernova occurs.
So this supernova is the first supernova.
That's right, that's right.
Okay.
This is just an idealized test with single supernova injection. But later I'll show in the more realistic simulation of a galaxy, we have a bunch of cluster supernovae going on. And you can see, as you said, the ambient density will keep decreasing as the supernova develops. So an alternative way to study the effect of supernova feedback is use the so-called ISM patch simulation, where you simulate a box around a kiloparsec scale, and assuming some idealized boundary conditions, often periodic boundaries, and then you can then reach very high resolution, so the parsec resolution that required to resolve individual supernova explosions. These type of simulations have been very successful in studying the phases in the ISM and star formation regulation in the ISM. So these type of simulations has a obvious drawback in their boundary conditions. So obviously, the real galaxies are not periodic, and by assuming periodic boundary conditions, you're going to miss the large-scale modes, for example, the spiral structures, the effect of just large-scale density fluctuation in general. So recently, it has become possible to simulate the entire galaxy and isolate the galaxies, achieving a similar resolution, the parsec-scale resolution. This is an example of such simulations of a dwarf galaxy. You can see this face-on and edge-on view, and this is a zoom-out edge-on view. And on the top, you see density, and on the bottom, you see temperature. And these type of simulations has the combined effect of both, the advantage of both. On one hand, it can resolve the small-scale properties, but it also can capture the large-scale information and allows you to study the outflow properties very far away from the galaxies. But I should also caution that because of the resolution is very demanding, the resolution requirement is so demanding, these types of simulations currently are limited to dwarf galaxies. So if you have the resolution that resolve individual supernova explosions, what you can see is that the properties will become, you can achieve numerical convergence. Here I'm showing you the outflow rate relative to the star formation rate as a function of radius towards the center of the galaxy. So at different resolutions, you can see between 1 and 5, they are almost identical. But as you go to, as I just said, at 100 solar mass or so, you start resolving supernova feedback, and that's where you start to see divergent results. On the bottom, you see a similar behavior for the energy outflow rate. I just want to mention that these simulations has recently been achieved for a larger galaxy, for the LMC. So the LMC is, although it's nominally a dwarf galaxy, it's actually more like a normal galaxies. So in the future, we will become to see these type of simulations for typical star-forming galaxies. So I think the point is that this will be an important methodology to study feedback and to study the ISM physics in the coming years. So because of this recent development, we decided to do a code comparison studies with 4 different codes. We have 3 Lagrangian codes, so particle codes. We have Gizmo, Arepo, and Gadget. We only have, unfortunately, only one Eulerian code, which is Ramses, with AMR functionality. So it simulate the same galaxy with similar resolution, and we have 2 different resolution. So the low resolution ones, the Eulerian code has 7 parsec resolution. The Lagrangian code has 100 solar mass resolution. And the high resolution one will have 2 times better spatial resolutions and 8 times better mass resolutions, which roughly corresponds to the same scale. And the value, so the way we chose this resolution is because for Lagrangian codes, if you use this resolution, then if you look at the highest density where you start resolving the genes mass, the gravitational collapse, it roughly corresponds to the cell size of 7 parsec. So we think these at each simulation set, the Lagrangian code and the Eulerian code have similar spatial resolution. And we try to keep the rest of the physics as identical as we could. So we all use the cooling from the graph code cooling package, assuming equilibrium cooling with a metallicity of 0.1 solar. And we include the heating from photoelectric effect from young stars on dust. And star formation occurs in a dense gas. And the way we define dense gas is we define a Jeans length, or in Lagrangian code, this will be a Jeans mass, where this length scale is smaller than your resolution scale. So that means you stop resolving the gravitational collapse. And once we stop resolving the gravitational collapse, the gas is eligible for star formation, and they will be turned to a star particle in a free fall time with a star formation efficiency of 1%, which is motivated by the observed star formation efficiency. And the supernova, the feedback, we try to keep it as simple as possible. So this is the pure thermal feedback, just naively injecting 10 to the 51 ergs into the surrounding ISM with a supernova lifetime of 10 million years. So this is a star formation rate as a function of time in a low resolution runs. So as you can see, all these different codes predict similar star formation rate within a factor of 3. So this is quite encouraging. So this means that different codes actually converge to similar answers. And also, I want to point out that this resolution is already very high in the standard of cosmological simulations. If you look at, for example, the fire simulations where they have the highest resolutions is around 500, a few hundred solar mass or so. So before that, we were about to publish a paper, and then we went to the high resolution one, and we see things start to diverge. Here you can see 3 different codes with very different star formation time evolution. And if you look at the Gizmo and Arepo, you'll see a very strong time evolution of star formation rate. So it's very bursty. But if you look at Ramses, which is a pink line here, it remains stable throughout the simulation time. So just by that, you can already conclude that these simulations are still not converged. So there's still very significant resolution dependence.
I have a comment about it. So the low resolution and high resolution only by a factor of 2.
Right.
But your result can vary at this factor of 3. But you can say it's convergent. So I think this low and high resolution probably maybe it's better to have more big difference, like a factor of 10 difference, to see the converging, to say it's high or low. But the factor of 2, I feel is very astronomers it's almost the same.
Yeah. So completely agree. So I think what's missing is lower. So we cannot push the resolution further for the high resolution one. But I think what's missing and would be interesting is to do like lower resolution
like
one.
a 10 parsec, 20 parsecs.
Like 2 times coarser resolution.
Yes.
See whether these things start to converge or diverge.
Yes.
I agree.
So do you know why the Ramses code seems to be converged by itself, but not the other?
The run. It seems to be converged. Yeah, I'll get to that. So the reason is supernova clustering, but I'll get to that later. This is a phase-on morphology of the gas, of the disk, of these 3 different simulations. So for the 2 simulations that show very bursty star formation evolution, that's Gizmo and Arepo. So you can see this very, this gigantic holes or bubbles is driven by supernova feedback. But if you look at the Ramses one, the high resolution one, you almost cannot see any bubbles here. There may be some like tiny bubbles, but it's unclear. So it's also drastically different in terms of gas morphology. Now, we did a numerical experiment by setting the supernova delay time to 0. So this is obviously unphysical, but this is for the purpose of numerical experiment. And interestingly, then we see that all codes behave very stable, so you don't see any bursty star formation rate anymore, even in Gizmo and Arepo. And now, if you look at your gas morphology, you see that none of them have this like gigantic supernova bubbles.
The morphology still looks quite different.
It's still, yeah, I agree. It's still a little bit different, especially the Ramses one, and but it's unclear what's causing the difference.
And my impression is that if for longer time it will be smooth out, but it doesn't look like, say, our Milky Way is much smoother. We don't have this fine, say, fine grain structure.
You mean like spiral arms?
Yeah, something like that.
Right. This is a dwarf galaxy, so we don't expect to see a very like grand design
So
spiral arm.
even if you run it for sufficient longer time, it still looks like this. So
Yeah, this is very steady state. So
Very
it doesn't
steady.
matter when we look at the simulations. It's more or less. So the simulation has been around for it's run for a giga-year, and it still behaves more or less the same.
So that's my impression is that for Milky Way simulations at earlier epoch phase, okay, when the system hasn't saturated, it does look like this. So
Yes.
very fragmentation. But once the system stabilizes, then it looks smoother. But you say it's because this is a dwarf gas.
I'm not sure about the Milky Way galaxies, but I'm pretty sure if we run this simulation for another giga-year, I'm pretty sure it'll stay roughly the same. So we don't see any evolution at all throughout the simulation of the giga-year simulation.
My impression is from that Agora comparison structure, right?
Okay.
Yeah.
Yeah.
So,
Yeah, that might be different. That might be due to different physics, but that's
No, I think maybe I comment the series the question. So if you simulate Milky Way galaxy, usually you will put the actual potential in the center, and that will driven actually later will develop into the spiral structure. The initially will look like this, but evolve maybe 1 or 2 giga-year, and you will great structure with Milky Way. But I think this dwarf gas it doesn't have light component, so it will do all the same all the way, if you like, always like this.
right. So if you put in a potential of the spiral arm, you will develop that pattern. But for a Milky Way type of galaxies, even if you don't put in any spiral potential by hand, it will still develop. These spiral arms will still develop. Right. So the main point is if we inject the supernova energy instantaneously after star formation occurs, then we don't see any bubbles, supernova bubbles. The star formation rate is very steady. Now this is great because it's a long-standing problem for idealized simulations where you have this artificial initial burst of star formation. So if you ever done a simulation of idealized galaxy, you'll notice that there's an initial phase where the gas collapses globally, so vertically, onto a very thin plane, and then star formation occurs, and this burst will kind of evacuate the entire disk. And you have to wait a bit longer for the gas to fall back. This is fine, but because the gas will fall back, but it will have to wait for a few 100 million years for the gas to fall back and reach the steady state again. So what we did is that in the first 200 million years, we used this instantaneous feedback injection to give us a smooth, a stable disk. And after that, after 200 million years, we set the delay time to the more physical 10 million years. However, even with this trick, we still see bubbles, but although with much smaller sizes in these Lagrangian curves as opposed to Ramses. So we can conclude that these holes, these bubbles, are not an artifact of the initial setup of the initial conditions. They're actually the physical from the simulation. Now, if we look at the sort of phase diagram, the gas density as a function, gas density versus temperature, we'll see pretty good agreement between Lagrangian curves and Ramses. You all see this, the majority of the gas is in a warm phase. And in a dense gas, as you go to maybe 100 or so, we start to see the classic S-shaped thermal equilibrium curve. And the star formation occurs around density of 100. This line represents the star formation threshold where the gene's length or the gene's mass becomes unresolved. So these gas will be unresolved and they can form stars. The point is that by comparing the fiducial model with the instantaneous feedback model, we don't see a significant difference in the gas distribution in the phase diagram, because the phase diagram is controlled basically by radiative cooling. So the key quantity to look at is actually the density, the environment where supernova happens. So this is a cumulative distribution of the ambient gas density where supernova explosion happens. So if you look at, for example, if you look at those dashed lines, these are the models with instantaneous supernova feedback. You'll see that they all happens in dense gas, about 100 density. This is by construction because we're forming stars in dense gas, and once the star is formed, we instantaneously inject supernova energy. So the reason that the fact that they are all happening in dense gas, this is just by construction, by design. But this design actually leads to supernova occurring in density of 100, so very dense gas, where radiative cooling is very efficient, which means that the supernova feedback will be very inefficient because all the energy available to create momentum is from the radiated wave. As a result, you see very stable this morphology in these instantaneous feedback. You don't see any supernova holes or bubbles. On the other hand, if we look at the supernova ambient density for the Lagrangian curve, so these three lines, you'll see, first of all, they agree very well with each other, so that's quite encouraging. But secondly, you'll see that there's a lot of supernovae that occurs in very diffuse gas. So this is 10 to the minus 2, and even lower. So 50% of supernovae occur in very low density gas. And this means that these supernova explosions will be, the radiative cooling will be very weak because of low density, and therefore the feedback will be very strong. But if you look at the fiducial model, the fiducial Ramses model, you'll see that it's kind of intermediate between these two. So it's systematically occurring in the supernovae in Ramses, in the fiducial Ramses, is occurring in systematically denser gas compared to these three Lagrangian curves. Now, if you look at the density where star formation occurs, this is again the cumulative distribution. If you look at the instantaneous models, these dashed lines, we see that they occur in a density of about 100 or a few hundred or so. And if you compare that to the solid lines, where there's a there's a 10 million years supernova delay time, you see the fiducial model. In the fiducial model, star formation occurs at much higher densities. If you look at the Lagrangian codes, so that makes sense because if you have to wait for 10 million years for the supernova to explode, the gas will have time to further collapse to denser gas, and that's what happens here. In contrast, if your supernova occurs instantaneously, once supernova occurs, there's no further collapse. You basically stop the collapse right when the first supernova exploded. However, the interesting one is a fiducial Ramses. It actually follows very nicely with the instantaneous model, despite the fact that it has a 10 million year delay time. So what happens is that in Lagrangian code, the gas can collapse as they cool. They can collapse, and they can pass the star formation threshold to much higher densities, and they can form stars there. However, in Eulerian codes, once the gas is past the star formation threshold, because the spatial resolution is constant in Lagrangian code, it doesn't actually collapse to higher densities. It actually stays there and wait for the free fall time and plus the efficiency factor, and can hang around there and then form stars. And that's why you don't see any star formation occurs at high densities here in Ramses case.
So you're saying that because the Lagrangian code has a higher spatial resolution?
Right, because for Lagrangian code, in order to collapse, you just move particles together, right? The spatial resolution will be by constructing increasing. But in our Eulerian code, if you reach your spatial resolution, in order to go to higher densities, you have to accumulate gas. You need accretion for the ambient gas.
But for the Lagrangian code, you have to some kinds of softening.
That's right. For the softening,
much smaller.
That's right. But the softening is actually, in our simulation, is actually set to the cell size. So the gravitational softening is by constructing adaptive.
So it's much smaller than the resolution in the Eulerian code.
That's right. That's another way to look at it.
In that case, why the Ramses code doesn't show any convergence? I mean, show a convergence result, but you increase the resolution.
Right. We call it a fake convergence because it's stabilized by the cell.
But the cell becomes smaller.
The cells become smaller, but it doesn't have very dense. So the star formation doesn't occur at very high densities. That means. So I'll get to that later. So the supernova will not be as clustered in the Greek code, in the Lagrangian or Eulerian. Okay. Let me skip this part. We realize the key of the difference is how supernovae are clustered both spatially and temporally. So we did a cluster analysis using the friend-of-friend algorithm to ensure that a cluster, all the members of the cluster will be physically, will spatially clustered, and they will also be temporally clustered. So technically, that means that we, in addition to the linking length of a 10 parsec, we also adopt a linking time to ensure that these supernovae actually occur in a very similar time. So this is a face-on map of the 10 most clustered supernovae in these different simulations. So each circle, each point is a supernova event. And here you can probably see like several supernova clustered together. And these lines actually represent the galactic rotation. So in the Lagrangian cone, you can see if you do the clustering number, so each cluster has around 200 supernovae in these clusters. And Arepo is even higher, so a few hundred supernovae in each cluster. But in Ramses, there's only around 40, so much lower clustering numbers in Ramses' case. So this is again due to the fact that star formation rate, the star formation occurs in a much denser gas in Lagrangian code, which makes them much clustered compared to the Ramses case. In Ramses, once you pass through the resolution limit, it will not keep collapsing.
Do you keep track of the stellar evolution?
The-
You do the initial mass function and stellar evolution rated, for different masses.
The stellar evolution
Yeah,
of
you said like 240 cluster supernovae,
right.
but they don't occur at the same time.
They don't occur at exact same time, but they occur in a like similar time.
It's not similar.
What do you
The
mean?
most massive stars explodes in a few million years. In the last,
Oh, I see your point. No.
57 years.
Yeah, so we do not change the stellar lifetime based on the initial mass. So we assume a
It would
constant.
be easy for you to implement some kind of initial mass function, use a different mass range and different delay time.
It should be quite straightforward. Actually, it has already been done, but in this project, we just didn't do that. So try to keep it simple.
So what's your time step?
The time sets are much smaller than. It depends. The time sets are
How
depending.
do you decide when to explode the supernova?
So they explode after 10 million years of the star formation. The gas particle converted into a star particle, and it has to wait for 10 million years, and then they explode as a supernova.
The most massive stars, like 30 solar mass stars, they explode after a few million years,
Right.
4 million years.
That's right. I agree. So that's
10 million years. That's P star.
So that's a simplification. So we're using a constant life delay time. So that's not the most physical model. But I agree, it will be very straightforward to include like mass-dependent lifetime. And that's already been done.
So explode them at similar time with similar ambient interstellar medium conditions.
No. It depends. It depends on the. So you can have a range of stellar masses in your star particles, right? And you can adopt the stellar lifetime based on the initial mass. So that has to be done in other simulations.
With the first supernova exploding some kind of regular interstellar medium, but subsequent supernovae will explode in a rarefied medium.
Yeah, that effect can be captured in this simulation. It's just that the delay time is not the most physical. Did I?
So there's no randomness in this delay time in this simulation.
Exactly. So there's no randomness. Right. So if we look at the models with instantaneous supernova feedback, we'll see the cluster is significantly suppressed. So the cluster, each cluster has like 5, some 10, or around 10 supernovae in each cluster. Let me skip this. So this is getting back to your point. This is for looking at one particular supernova cluster, but each symbol represents the ambient temperature and ambient density. A different color represents different clusters actually. So there are 4 different supernova clusters. But the first few supernovae occurs in dense environment. But as time evolves, because of this clustering, you'll carve out a hole, and the subsequent supernova will occur. And that's that's where you see this ambient density decreasing as a function of time. And by the end of this lifetime, the ambient density can go to as low as 10 to the minus 2 or 3. And also they occur in a very high temperature, so very hot gas, heated up by previous supernova. So that effect can be captured. Let me also skip this. The final point I want to say is that we just see that we can make the Lagrangian curve to be very numbersy by setting the delay time to 0. Now we want to ask, can we make the Eulerian curve as bursty as the Lagrangian curve? Now we realize that if we check the supernova, the star formation efficiency from 1% to 100%, we will significantly increase the clustering of in the Ramses model as well. They will be as clustered as these two curves. So this will make them as clustered and also make them bursty. As you can see here, with 100% star formation efficiency in the Ramses one, you also see these supernova bubbles. Now,
won't you create too many stars?
what's that?
Won't you create too many stars?
The star formation rate is actually not that different, so it will be significantly higher.
But
But
increased by 100%.
oh, it won't actually. So the star formation rate won't be increased by 100% because of cell regulation. So you increase the star formation efficiency locally by 100, by a factor of 100, but you're suppressing the star formation in other places in the galaxy.
So the overall star formation rate
Yes.
is still about the
It
same.
is comparable. So this has a very significant effect on the galactic outflow rate. If we look at the outflow rates measured at above and below the midpoint at 10 kiloparsec, we can see that the Lagrangian curve has this significantly stronger outflows with a fiducial setup. And if we turn the delay time to 0, the outflows disappear. And for the Ramses one, so the Eulerian curve, the fiducial one has a much lower outflow rate compared to the Lagrangian curve. But we can make it stronger by either increasing the star formation efficiency, which will be this one, or increasing the supernova lifetime artificially to 50 million years. But as we just see, this will increase the clustering. So the bottom line is that the outflow rates are also controlled by supernova clustering. So this I'll just leave my summary here and I'll take questions. Thank you.
Okay, questions for Chia-Yu?
Guys, thanks for the nice talk. I just have a comment. So I think this is actually the core comparison, because the key thing about the different result from the Lagrangian and Eulerian code is due to, I think it's due to the star formation recipe. So I think star formation recipe plays quite an important role in comparison, because this will define how many and how massive of this star can form in a galaxy in which way. And I think the star formation recipe in Gizmo and Arepo is different. That's slightly different from the Ramses in the.
No, we set the star formation recipe to be the same.
But I feel this. You see the result from this because you see the bubble original normal one. You see the bubble from this Lagrangian code, and we don't see the bubble from the Ramses. This code was due to, you say, the star clustering. The star clustering should be due to the star formation itself.
Yeah. So it's coming from star formation.
Yes.
It's because star formation is cluster in the first place,
Yeah.
which leads to clusters supernova explosions.
Yeah, so intrinsic different from this is not, maybe that's not actually due to the code, but it's due to the star formation is different. Which can be due to the code, but the which can be also due to the way when we set out the star formation. Because I think you probably don't resolve, you don't resolve the individual star.
Yeah,
You resolve is like a star cluster.
We have set up mass resolution around like 10 solar masses. So it's close to individual stars. But we're not resolving like the formation of like the initial mass function. It's not something we can predict.
But if that's the case, how did you form massive stars?
So we sample the IMF. For example, if we have a solar mass with a resolution of 10 solar mass, then we will sample a massive star progenitor every 10 particles. So every 10 particles, we will choose a particle to explode as supernova, such that there's roughly 1 core collapse supernova per 100 solar mass. So it's stochastically determined.
Yeah, because I was wondering, individual particle has fulfilled the star formation criteria, and is that particle 10 solar mass fall into a star, or how does that work?
So each particle has the same. All the particles have the same mass, roughly the same mass, and once they pass the star formation threshold, they will be converted into a star particle in a free fall time.
What's the mass of the star from that particle?
It will be 10 solar mass per particle.
But we are.
Nature doesn't work that way.
Yeah.
What's that?
Nature doesn't work that way.
We didn't say this.
Not all stars are the same mass.
Exactly. Right. So we're not trying to sample the star cluster. We're not trying to study the initial mass function. What we are trying to do is to identify regions where star formation will happen, which we can resolve. That's the cloud, the molecular cloud. And the individual stars will not, the stellar dynamics will not be modeled properly. Like the collisional dynamics within the star cluster will be wrong. But we can follow how much star formation is occurring in different areas.
But the cluster size usually just a few parsecs, even less than a few parsecs. So it's all within your one cell.
The cluster size.
Yeah. When a cluster is formed, the entire cluster is only like a few. So what's your resolution? Like 100 parsecs?
The resolution is either 7 parsec or 3.5 parsec.
7 parsecs is already larger than the size of a cluster, the core of the cluster. The most massive stars in the cluster are usually in the center.
Right. So we might
within your one cell.
we might overestimate the size of the clusters. I think the main point of this work is not to say that this is like reproducing the nature, but it's to determine it's as a numerical experiment, like what's the physical mechanism that decide the different behavior in the galaxies. So we are not resolving the dynamic of the star cluster, but this is not our goal.
I don't care about dynamics of star cluster, but the stars in the cluster, they do explode to form your supernova.
Right.
Supernova.
The size might be, we might
And they're all
overestimate
within your
the
same
size.
cell.
What's that?
It's all within your same cell.
It's within the same
I
cell,
don't know how
but
you deal with the real physics of that cell.
it's within the same cell. But even if we're overestimating the size of the clusters, the systematic difference between these two different codes still applies. I mean, what I'm trying to say is that even if we have the resolution, to resolve this properly, we will still see the same effect in these two different codes. Does that make sense?
So you're concluding that the codes are not trustworthy?
I'm concluding that they are systematics between these two codes.
So
and
which
you can
one
put
is-
it that way, but I'll say that they are like future studies to be done.
Yeah.
No, Chia-Yu, just a comment about this because I think your resolution actually is very nice and very good. But the key thing, the simulation is not about, oh, we can put the resolution to the optimize to infinity. But instead, why we need high resolution? Because we want to resolve the physics which involve in the scale.
Right. So in
but-
our case, it's the supernova explosion.
But the key thing is, I think the key result, quite the different, make the two different between the code in the supernova physics is intrinsically in the physics. It's not in the supernova physics, but in the star formation physics. And that star formation physics will depend on the code nature itself. But the key thing, think about one thing. If you have one particle, it's 10 solar mass, and it has a size about 3 or 7 parsec. But in the reality, in that 7 parsec is already a star cluster. It's more than 10 solar mass. It's 100,000 solar mass, in which the supernova will explode in light particle. It's actually what probably look like this in the nature. So the key thing I want to convey with this is this point.
So I think, so let me say something about Chia-Yu. I think it's fair to say that they are resolving the subsequent spatial distribution, like second and third generation star forming clouds. So their spatial locations differ by a lot, right? So if you don't have that initial stellar feedback, and then the second and third generation of star forming cloud will still look quite homogeneous. But you can see that they clearly resolve that when the first bubble goes up, and then the second generation of GNC is quite clustered. Therefore, the galaxy can be continued to be bursty. Right. So I guess that's kind of what affected the galactic scale feedback, right? And also, for example, it sounds like the total mass loading rate, and then how strongly the outflow can escape this kind of thing. So I have one follow-up question on that. So are there any observations, for example, nearby galaxies, star formation history or mass loading that you can compare with to say what kind of a level of outflow is more reasonable?
Right. So there are observations. So observing outflows are very difficult.
Mm-hmm.
There are recent observations of dwarf galaxies quantifying their outflow rate from H alpha.
Mm-hmm.
And it seems to be on the lower side. So it seems to be more comparable to our outflow rate as opposed to the very high outflow rates as used by like cosmological simulation.
Mm-hmm.
But the data, we don't have much data for outflow rate to compare with.
So you mean similar to your Lagrangian results?
Right, for the Lagrangian case.
And then so you think the Eulerian codes looks like it's not producing sufficient starbursts.
So the fiducial one has a very low outflow rate. Whether that's physical, we don't know.
Okay. Are there any final questions for that?
Maybe I can have a follow-up question. So could you go back to the phase diagram? I'm just curious, because if you look at the Ramses code, the number of particles with the mass passed through the star formation threshold is actually lower than other codes. I'm just curious whether or not this is a consequence, or actually it's a similar effect as Ken just mentioned, because the setup of the code that prevents the more gas to form stars, and therefore there are not as many clusters in supernova compared to other codes.
I think this is just a consequence of the behavior of gas once it passes the star formation threshold, right? So we just discussed that in our Eulerian code, once you pass through this star formation threshold, you don't keep collapsing and collapsing to higher densities. So that's why you don't see much gas here, as opposed to the Lagrangian code. I think that's just due to different behavior in gravitational dynamics.
Okay, but I'm curious about whether the amount of gas that can pass that threshold, whether or not actually the effect is not like passing the red line. It's actually before the red line there are already some effect that will affect the cooling of the gas or something and change.
Right, you're saying that this looks a bit brighter than the others, this area?
Yeah, I'm just curious about the amount of gas that can pass that threshold, whether or not the way of simulating this will affect.
So the amount of gas passing through should be quite comparable to Lagrangian code, because we see that the star formation rates, their star formation rates are similar, and that's determined by the gas that's just passed through the star formation threshold. I know it looks a bit brighter compared to the others, but we actually check the density PDF, and they are actually similar.
Thank you.
So these two behaviors, which one is more fit to our nature?
Yeah, it's a great question. Yeah, so formally speaking, once you pass the resolution limit, both codes are not trustworthy, right? Both codes have different numerical artifacts. You can say grid codes are not collapsing enough, Lagrangian codes are collapsing too much. But I think the goal is to reach the resolution where this difference becomes small enough. So right now it's unclear, and it depends on what properties you're after.
But I'm still a bit confused because you say it's because of the limited or lower resolution in the Eulerian code. And why does the increasing resolution help? You say this fake convergence.
Yeah, so imagine we have infinite resolutions, and we can resolve to infinite high density. Then they should converge, right? Because they all have the same resolution, which is infinitely small.
Yeah, but why does it increase resolution by a factor of 2? Doesn't help at all.
I think that's because it's still far from convergence.
There's no trend to converge.
No, yeah, exactly. So we think it's still not close to convergence at this resolution.
Yeah, I'm not saying it should converge, but it should give you some hope, right? Say if you increase it further, it will become better and better, but there's no sign of that convergence.
Yeah, I agree. So ideally, we would like to have like a systematic, like maybe a few more, like 2 or 3 higher resolution rounds, and see a trend. Right now, we only have 2.
Yeah, but my question is, even with only 2, why can we see this trend? Even if the Eulerian code still behave, say, worse compared to the Lagrangian code, but it should get closer, right? Even just a little bit.
Right, but as the resolution, no, there's another effect coming here. As your resolution becomes closer, you also make your supernova less resolved, so they become less efficient. So I think that's what happens in our low resolution simulations, where supernova explosions are unresolved in both codes, and they are both inefficient because of numerics. So that's why we see that opposite trend. So if you go to much coarser resolutions, they will all become very stable and numbersy because you don't resolve the explosions.
Okay, so I suggest that we can move the discussion outside, so there should be tea and snacks. And let's thanks Chia-Yu again.